This video is an example problem with motion in one direction, horizontal direction I should say. There's going to be two parts, some motion to the east, some motion to the west, but we're on a straight line on level ground, and we're in a car where the engine is not applying force to the wheels, so we're just coasting and no friction, no air resistance, just a simple basic motion problem. I'm going to let east be the positive direction. The car is at the start of this problem traveling east at 80 kilometers per hour, but we're about to apply the brakes, and the brakes can apply and create an acceleration of the car of minus 5 meters per second squared. Why is it a minus? Because the acceleration is going to be towards the west. We're slowing the car down. The car is traveling east right now. We're going to slow it down. So let's compute the distance required to stop the car with the brakes. And then suppose that somebody puts their foot on the brake pedal for 8 seconds. What is the final velocity of the car? So those are the questions that we want to answer, and we want to do some thinking along the way. So one thing I'd prefer to do here is, instead of working in kilometers per hour, I'm going to convert the units to meters per second. So 80 kilometers per hour, if we go step by step here, there are 1,000 meters in 1 kilometer, so we'll get the kilometer units to cancel out. And then 1 hour is 3,600 seconds, so we'll get the hour units to cancel off. You ought to pause the video and check with your calculator. I come up 22.22 meters per second to the east. That's the velocity of the car at the start of this problem. Well, we've got a lot of equations for kinematics, even if we're just doing one direction, horizontal direction. There are 4 kinematic equations. V sub x, that would be the final velocity in the x direction. Vx naught, that's the initial velocity in the x direction. The acceleration in the x direction, and the time interval. So that would be our first equation. The second one has the displacement here. Final position minus initial position is equal to 0.5 times final velocity plus initial velocity multiplied by time. And the third kinematic equation, again, you get final position initial minus initial position, the initial velocity multiplied by time plus 0.5 times acceleration in the x direction. This is a horizontal problem on a level road, so it's the x direction, not the y direction. And then t squared, where t is the time interval involved. And then lastly, final velocity squared equals initial velocity squared, 2 times the acceleration times x minus x naught. How do we pick the right equation? Which one's going to be useful? Well, we list out what we know. We know that we can put the initial position anywhere we like. So I'm going to put the initial position when we start to apply the brakes. So x naught, and that'll be 0 when we start to apply the brakes. When we start to apply the brakes, we now have an acceleration of minus 5 meters per second squared. Something very important in these equations, you must think about your problem. The acceleration must be a constant. When you use any of these 4 equations, the acceleration must be a constant. If the acceleration changes, you're going to have to do the calculation separately for each separate acceleration value. And if the acceleration is continuously changing, switch to calculus. This video is being done for a pre-calculus level physics course. So takeaway here, acceleration must be constant. The final velocity of the car, while we're using brakes, the final velocity of the car will be 0. We want to know how long it takes to stop the car. Our initial velocity is 22.22 meters per second, a positive value because east is positive. Well, which equation will you pick? Well, if you start putting numbers into these, we want to know the distance required. We want to know what x is. Excuse me, first kinematic equation doesn't have x in it, so that one's not going to be any good for us. We could use it to calculate time, but this we're commanded here to find the distance, the final position x. So the second equation has two unknowns, x and t. We're not going to use that. The third equation has two unknowns. We're not going to use that. The fourth equation is the one we want to use. We know the final velocity, we know the initial velocity, we know the acceleration, and we know the initial position at the start of our analysis of this problem is 0. We're looking to calculate x, so that fourth equation will work. So again, I'm just repeating out here the fourth kinematic equation in symbols, and now putting in the numbers. The final velocity is 0. We're stopping the car. Initial velocity, 22.22, and then the acceleration of minus 5 meters per second squared. Very important that you do have the minus sign here. The acceleration is in a opposite direction to the velocity. This car is traveling to the east. The brakes work against the velocity, so we have a negative number for the acceleration. And you might want to pause the video and pull out your calculator and double check my work here. I think 2 times minus 5 is minus 10. And then I move this term to the left side, adding 10 meters per second squared times x to both sides. So we now have 10 meters per second squared times x equals 22.22 meters per second squared. When I square this on the right, I square the number, and I also square the units. So meters squared over second squared. What's happening with the units on the left side? Well, this meters per second squared, those units are coming from the acceleration calculation. And I have a multiplication by meters of x as units of meters. So I'm going to get meters squared over second squared on the left. I have meters squared over second squared on the right. We're consistent. We're not fouling up our units somehow. And now divide by 10 and rounding a little bit, I get 49.4 meters for the final position of the car. So it's traveled 49.4 meters to the east when it's now stopped. Part B. Again, our car is traveling to the east at 80 kilometers per hour. If the brakes are applied for 8 seconds, what's the final velocity of the car? Well, we don't know at 8 seconds where the car is. The x minus x naught quantity is unknown. This calculation we just came through, when the car was stopped, we're 49.4 meters down, but this was not at 8 seconds. We did not know the time. We picked a fourth kinematic equation that doesn't have to have time in it. So 49.4 meters, that's not associated with 8 seconds. X minus x naught is unknown. Well, with that being unknown, we can't use these last 3 kinematic equations. We're trying to calculate the final velocity. We do know the initial position is 0. We know the acceleration is minus 5. We know the time is 8 seconds. So equation 1. And we come down here in 22.22. Then the second term, minus 5 meters per second squared times 8 seconds. Multiplying seconds onto a division by second squared, we now get to meters per second. Note that these two terms have the same units. That must be the case. You can only add coefficients together that have the same units. So we're getting that value of 22.22 minus 40. I come up with a velocity of minus 17.8. Minus 17.8 meters per second. We've been applying the brakes for 8 seconds. What's the minus sign indicate? Well, we chose east to be the positive direction. This car was moving initially in the east direction, in the positive direction. Now the velocity is a negative number. We pushed on the brakes. It's the only thing we touched in the car's mechanism. And now the car is traveling 17.8 meters per second towards the west. You should be surprised at that. We're stepping on the brakes for 8 seconds. Well, we step on the brakes for 8 seconds. I chose 8 seconds because I knew it was longer than the time to actually stop the car. So the car is going to be stopped. The final velocity is 0 meters per second. And then we keep pushing on the brakes. Nothing happens. If the car is not moving, the brakes do not accelerate the car. Brakes only take away velocity. So the final velocity is 0 meters per second. encourage you to think as you work through the mathematics. The mathematics is all good. I came up with minus 17.8 meters per second mathematically. Didn't make any errors in the calculation, but physically, it's not meaningful. In working physics problems, you have to actually do more than mathematics. You have to think about the situation and apply your physical understanding. Brakes can only stop cars. Brakes do not make cars reverse direction. Well, more videos in physics and astronomy and other miscellaneous topics can be found annotated, described at gpclements.com. I tell you the name of the video, a short description, how many minutes long the video is, and there's a link directly to YouTube where you could watch the video. All this content is free. You're not allowed to resell it, but it's all free. You do not register. You don't give me your email address or any other information, and my website does not put cookies on your computer. So enjoy this and ask your instructor if you have questions.